CMP 2250 screen, right?
Yes, yes.
Yeah, okay. So the first thing we're going to do here, we're going to go to the content and then go to tools and documentations. Okay.
Okay.
So I think I'm hearing myself back. So if you could maybe mute your audio while you're not talking. Yeah. All right. So um, so in tools of and documentation, we have a bunch of stuff here, but I want to just make clear the bare minimum that we need for the course. So first in Seger tools, there are two things that we need here. Well, three actually. So one is the link to Seger Embedded Studio, which I assume that you probably downloaded this at home. I'm not so sure, but you can download the software from here. This is actually not the latest version, but is the one that works. So I suggest we just use this one for now. So we're going to need the installer for Seger Embedded Studio. That's the one. We're also going to need the J-Link software. Okay. And we're also going to need the ST Reflash utility. All right. Okay. So these are the tools from Seger. Let me just, so I'm not so sure which version I have installed here. Yeah. Well, I have these tools already installed, right? So this one is the setup for the IDE. Okay. So this one I already have it installed, but basically you just execute this and follow the steps, just keeping the defaults, no issues there. Same thing for the J-Link software. After Sega Embedded Studio is installed, we have to install this J-Link software. The J-Link software I have, in my case, is a bit outdated. So maybe I'm going to, if you give me just one moment, I'm going to uninstall the current J-Link software and do that one so we can do it together here. Just going to uninstall that one and do that process. So I'm assuming that we already installed Sega Embedded Studio, which is the IDE, right? So this is the version, and I already have it here installed. So assuming that we did that one, so now we go and install the J-Link software, okay? So we just hit next, next, agree. And the defaults will work for your home computer. However, if you're ever installing this at any of the labs at NATE, although this software is already installed, but if you're ever installing at any of those lab computers, we need to set up install for this user only, okay? Because this one will require admin rights, but since we have those admin rights here, there's no problem. We can just install the full version, okay? So this is the software that is needed for the debugging and for the drivers and all that. Okay, so we just leave everything as default there, not a problem, and we finish. Now, this J-Link reflash utility is just a portable thing that has to be extracted. And it's just a simple executable. And it's just to convert our debugger from a ST-Link to J-Link. Here's the thing. Let me just bring up the camera.
Okay.
So this is the board here, okay? The board has its main microcontroller here, but this other microcontroller here is actually the debugger. All this part on the top is a debugger. So that's equivalent to what we know in our old microboard as a BDM pod, okay? So this is the one that's going to do the debugging. So this guy actually needs also a firmware to be running, okay? So, and this tool here is the one that converts the ST-Link to J-Link, okay?
Yeah.
Now, before we do that, actually I forgot, but these are the tools. Maybe let me group all these tools in a folder that's called Seger. I'm just going to move all this here. And let's go back to our write space. So in tools and documentations, I showed you the Seger tools, but we also have some ST tools here. And we have two tools that we're going to use particularly for now for getting started. Is the Q programmer is the one that we need. Okay.
Yeah.
And the Q programmer, why is it needed? Is because that installs the drivers for ST-Link, which I already have installed. Okay. But this one is also required. So I'm going to just move this one out of here. So we're going to put a folder here that's called ST. And extract this one here. Now, let me see if I have this one installed here. STM32Q programmer. Oh, I don't think I even have it installed. Okay, so good. So then I'm going to install this one first.
Yes. Sorry.
So the Q programmer, I'll explain in a moment what it is. Let me just install this one. Accept the terms. And this is going to be by default installed there. I'm just going to overwrite it because I think I already have it installed. That's why. Okay. Let's just give it a moment there. Oops. It wants me to do this. I'll just finish. Just move this out of the way. Okay, I think it's done there. Okay, so it's done. Let me just a moment here. Okay. So when we first purchased, I was just restoring the board to the defaults. So when we first purchased the Nucleo board and we plug it into our computer, it's going to bring up this virtual unit here, but most likely it's going to display somewhere in here in the COM ports an ST-Link virtual COM, and somewhere here in the USBs should display an ST-Link debug. Now, if it doesn't display that, it's because we haven't installed this STM32Q programmer that I just installed. Why? Because this guy actually comes with the drivers for ST-Link. So I guess this is the first thing that we should be doing, installing this one so the board can be recognized properly. Okay. Give me just one moment here. I'm just trying to close some stuff that I have open here. Okay, so let's open this again. Okay, so it opens this window. And this guy is used for flashing a binary, but we're not really going to use it for that. We're just going to open this tab that says firmware upgrades. Okay. The thing is, when we install this Q programmer, it will install the drivers already for the ST-Link. So after we install this STM32Q programmer, we should be able to see in our device manager this ST-Link popping up here when we connect the board. If for some reason shows as an unknown device, it's because this STM32Q programmer hasn't been installed. Okay, so once we have that, we can open this firmware upgrade here, because most likely we want to upgrade to the latest firmware of ST-Link before we can do the conversion to J-Link. You see, so we open in upgrade mode. And that tells me, well, it doesn't want to recognize it. Let me just open this and connect it again. Okay, so let's open in upgrade mode. Okay, so it shows me that my current firmware is, the version I have is M30, and it wants to upgrade to M32. Okay, so I can do this upgrade. And again, all this is doing is just upgrading the firmware of the debugger that I was just showing. And in fact, we're not even going to use ST-Link, but it's better to upgrade to the latest one before we do the conversion to J-Link. Okay. So the upgrade was successful. If I press on this again, well, it's showing that unknown. Just try again. Maybe connect it again. Yeah, and it shows me now that my version is 32 and it's the latest one is 32, so that's fine. So that means my ST-Link is working. So once I have this working, I can go to this. That's the only thing I need STM32Q programmer for as of right now. So I'm going to go to my tools that I downloaded from Brightspace. I need to go back to that folder. Winter. So in the tools, I need to go and send to the Seger tools and open this ST-Link reflash. Remember, this one has to be unzipped from here. So I open this guy, and it's going to open this DOS window, and I have to select accept twice. And I'm going to pay special attention to this here. I'm going to put this one on the side. So the device manager that right now is showing me an ST-Link, as you can see here on the right. So I'm going to say that I'm going to upgrade my system to J-Link, because J-Link is the debugging software that we want to use. So I'm going to say 1. And it's going to upgrade this firmware, and now it's going to change the ST-Link to J-Link. So, if you look on my right screen here, so my virtual COM port no longer shows as ST-Link, but it shows as J-Link, same as the software somewhere here, J-Link driver. Okay. So this is the state that the board needs to be at. However, there's a couple of issues here that I've seen in some computers, and it's happening in mine when you first install this, that for some reason does not recognize the J-Link driver properly. So what we need to do here, we need to right click on this and say update driver and browse and give the location of where the J-Link software is installed. So that should be in your C program files. Then go to Seger. And then we go to J-Link and we just select J-Link. Okay. And that should upgrade the software. And that should show up properly. I'm not so sure why it's showing up like that. Well, that's the procedure we have to do. It looks like it's working fine, though. We're going to be able to find this once we create our first project. So we'll just leave that for now. But in your case, if you see this with an exclamation or it doesn't recognize it as a J-Link, we need to update the driver and point to the proper J-Link software. In this case, for some reason, it's showing with an exclamation. I'm not so sure why it's doing that, but it looks like it's working fine on my end. Okay. So that is for setting the debugger on the first step. Then I'm going to start by opening Sega Embedded Studio and create the first project to at least know how to do it. So every time I open Sega Embedded Studio, it will open the last project that I had. If I've never opened Sega Embedded Studio, it will have like a default project. So in this case, I'm going to go and say start a new project, because that's how you actually always start a new project. So go to File, New Project. It brings this window, and we always want to create a new project in a new solution. Okay. Now the defaults here are not the best, so we have to give it a path to this because it doesn't really save the last path that we used. So I'm just going to put a folder here called samples. And also, when we create a new project, it does not create a folder for us. So we have to create as a folder. I'm going to say demo project 1. Okay. So I select that folder, and I'm going to call this one, also have to give it a name, demo project 1. Now, one of the things here is when you scroll down, you should see this SD. I'm going to save this path for later. You should see this SD group here. If you don't see it, it's because the package for SD hasn't been installed. So you have to go here to the package manager. Okay. Other way to get to there is going from tools, here, package manager. And then we look for STM32G, and we should see the G0XX popping up, okay? And in my case, it says that it's installed because I already have it installed. But if you don't have it installed, let's say I want to install now this package, you just toggle this from not installed to installed by clicking, and then you go next, and that installs the package. So remember, the package that we need for this micro is STM32G0XX, all right? Any questions so far?
Oh, that's good.
Okay. So then, provided that I have the package already installed, I can start my new project now. So again, new project. And I'm going to choose the location I had from before. And I'm going to name this one project demo 1. And then I have to select the first one here. It's a C, C++ executable SD microelectronics STM32G0XX. And by default, it's going to select this board here, which is exactly the micro that we're using, so we don't have to change any of that. Some of the things that we would like to change, if we are using printf or sprintf for any testing purposes, that is not enabled by default, so we have to enable this to float. The width precision, in case we're going to do percentage 04D or something like that, we also want to enable that. And scanf also, if we want to send something or do scanf. So we probably want to enable all those. Okay. Everything else can be left at default. And then next. And that creates my new project. And in my source file, I do have my sample main file. Okay. And of course, this is just doing a simple printf. So if I run this project, see the project by default, if we go to the right clicking here and go to options, by default, this should use the debugger as the target, JLink, see? But we could also change that to ST-Link, but remember in this course, we're going to be using JLink, which is why we did the conversion, okay? So that works fine. So this project should be able to run, okay? And if I run this, it's going to bring up the JLink software here, see? That means that it's working. So I can check that so it doesn't happen again. And accept, and is now running. However, it's not doing anything to the micro. If we run this, we have to click play there. We see that it sends hello world to this virtual console. Now, we couldn't do this in the old micro, right? Because the old micro wouldn't support printf. And it's very common that a micro doesn't support that because the printf is expecting a console, an actual console application to show that on the console. And the micro itself doesn't have a console, which is why in the older micro, we were doing sprintf and printing to an array of characters and then sending that to the LCD or to the serial ports. In this case, we do have a virtual console built into Seger. So only when we're debugging, we can actually use the sprintfs to print in this console. And we can also do a scanf if we wanted to send something from here. But this is just for testing purposes, and it will work only when we're doing debug. Because right now, even though we flash this program on the micro, it's not really doing anything because we're not targeting the registers of the micro. Okay? So I'm going to delete this now. And I'm going to do the same thing, the first thing that we have to do here. Maybe I'll leave that printf hello world just because when you are including a library and you are not using it, it shows this red squiggly here. So because I'm just going to print hello world without %d because I'm not printing any number, just that. And now this one doesn't show with the mark there. One library that we always have to include so we can access the registers of the micro, that's equivalent to the derivative file that we were using for the other micro, is this one. And it gets included with double quotes. It's the STM32 G0B1XX. So that is the library that we're always going to have to be including. Okay? And so before we include this library, then we can access the registers on the micro. For example, if we wanted to access the GPIO, we can then target the register in particular. Let's say we want to target this particular register. And we want to set a bit there somewhere. I'll explain what this is about later. For example, that. And then the first thing to ask, why are the registers looking like this compared to the other micro where we had only underscores? The reason is we can navigate through this and look at this definition. So if we go to the definition, that is defined somewhere here in this library. And the GPIO is a macro that is to a pointer to a data struct. So if we look at this data struct, is a GPIO data struct. And the reason why these things are organized in data structs is because we have so many registers that they are grouped by peripheral. So any GPIO, which was equivalent in the other micro to the port A, port B, port C, is in this GPIO type def, where all these registers inside are related to the GPIO data struct. And since this thing is defined as a pointer to a data struct, that's why we use the arrow operator to access the register inside. Okay?
Yeah, yeah.
Yeah, go ahead. Question?
No, everything is good, clear. Thank you.
Okay, perfect. So that's how we're going to be accessing the registers on this micro. Okay. Now, to start a new project here, I'm going to do something very, very, very simple. And for that, I'm going to give you, and I'm going to put all this in a repository that I'm going to create. I just did not set it up because of time, but I'll do that after I'm done this, and I'll give you guys access. So let me just give me a moment here. Let's find a demo. Maybe which organization could look. I could look actually 1250 organization. I can also give you access to you guys to all the repos on the 1250 organization that I have from last term, so you can actually look at those demos, right? I think that would be very beneficial. Let's see, in-class demos, I think are here. Maybe I'll look at a different one. Just one moment here. This one. And firmware projects. Oh, I just started project here. There are two lines that we are going to have always in any project. Okay, so in the initialization part, one line is this one. So, and that is whenever I put something, I will add a comment that links to the reference manual where that is discussed, and I'll show where those resources are in just a moment. The first one is this one that has to enable the power interface. One of the things that we have to understand with this micro is that since it's low power oriented, by default, everything is disabled, okay? Everything is disabled. So we have to enable it by connecting it to this clock. And the clock controller, and reset and clock controller, we can also look at the definition of this. See, go to the definition like we did with the other one. And it's a pointer to this type of data struct. And again, all the registers inside this group are in here. Okay. So this register has to be enabled most times, so which is why I put it there. The other thing that we have to enable is this. For example, if we want to enable the port A to be able to use GPIO A, we have to enable it like this, connected to the clock. And if we want to enable the port B, we have to do the same thing. So every single peripheral that I want to use in this micro has to be connected to the clock and enabled here. Okay?
Okay.
Now, where are all these things defined? I guess I haven't shown that yet. So let's go back to our table of contents here. And then we go to tools and documentations. And then we go to the development board here. And this is actually very important. I'm going to close the other two windows. There's a picture of the board here, and there's a picture of the pinouts, which is very important because, for example, let's say that I want to toggle port A pin 5. So I'm going to look here for PA5, which is right here, is on the 6th pin here. That is also together with this 11 pin. So the ones, the column here on the inside, the dark blue, is actually connected to the light blue. So it's the same. So for example, PA9 is present in this female pin 1 as well as in this one. Okay. So if I wanted to connect to PA5, I could connect to this 6 or to this 11 here. The outside ones are not connected to anything else. So if I wanted to target PA5 here, so in my board, I look at the board, right? And I look at this PA5 that is, I start counting down here till I locate that pin. Okay? So that information is here. And all the information related to the development board, to this nucleo board, is in here, including the schematics. For example, you can click on the schematics here and it will open this. Now, if we look at the schematics and we try to find this LED that the board has somewhere, this LD4, we can see that this guy is connected through a transistor and is connected eventually here to PA5, as you can see. So if I want to toggle this LED, I should target PA5, which is port GPIO A pin 5. Okay. But most importantly, in here, let me just go back. The information for the microcontroller is down here, and we have two documents, the datasheet and the reference manual. So the datasheet is for showing some specific information about the micro and for something that we're going to discuss later, which has to do with the alternate functions, okay, these ones. But that's it. All the information about registers and stuff, like we were used to see in the Big Pink or the other reference manual that we had in the older micro, all of that is in this reference manual here. And for example, if we want to go to the GPIO, okay, we go to this GPIO chapter 7 here. And if we expand that, we go to the GPIO registers, and we see all these registers the same as the way we saw them in the older micro, right? The only difference is that these registers are more complex because, as you can see, they're bigger. They're 32 bits, where most of the registers in the other micro were 8 bits. So these registers here, most of them are 32 bits or 16 bits at least. Okay? Any questions so far?
Good.
Yeah, so this is important. So somewhere in the RCC, so if you want to have more details about why I'm doing this, you have to go to the reference manual. See, you go to the reference manual, chapter 5.4, and we look at this, chapter 5, item 4, see, and it talks about these RCC registers, and here's where you enable all these things, okay? What was it actually? 4.5.15, so it will be this one. And it shows you in this peripheral all the peripherals that can be enabled here, including, of course, somewhere in here, GPIO GPIO A, B, and C. No, that's in a different one. Actually, this is for the power interface. But for the port A, maybe we should find this one and put it here, at least for the GPIO A. Let's see where that one is in the reference manual, so you guys can reference that easily. That is in the IO. Where is that one? This one. So that would be 5413, and that is where all the GPIO bits for the enable are. For example, if I want to enable GPIO A, I have to enable this by writing a 1 to the bit 0. See, same for GPIO B, whatever. Okay, bit 0, bit 1, and so on. Here is using only 6 bits. So that is 5413. So I'm going to put it here. Same for this one. So as you can see, this mask is actually setting that bit. How can we know what that mask is doing? If you hover on it, it shows you that in reality, that's a number 1. If you look here, whatever it pops up there, it says 0x1UL, bit shifted to the left by 1. Okay, so actually the port B is setting the bit 1, whereas the port A enable is setting the bit 0, see, because it bit shifted to the left by 0. So all these masks actually contain, if we go to the definition, they are defined here, and they have to do actually with these bits that get enabled here, sets. Okay?
Yeah.
All right. So another way of accessing this information, if Brightspace is not clear enough in terms of how to access this, you can also go to my site. It's where I have my lessons. It's just in carlosestre.com. And you may find this information here in the 1250. And you will also find it, of course, in the 2250. However, the lessons for 1250, since I still don't get to that point yet, I'm going to start discussing now this coming week. I'm going to add more lessons here. But all the legacy ones are in this part, G031, K8. And this is why I grouped them here, because last term we were using the smaller board. So we were using this one, which is pretty much the same family, but it's just a different board. That's why I put it in the legacy. Now, 1250, the 1250 this term is using the same board as you guys in the 2250. So the information is going to be consistent. So you can always check the 1250 information here. And in this part here where I talk about the Nucleo board, I also have the schematics and the user manual for the development board, as well as the data sheet, right? And the reference manual, the same that I was just showing. It's also available here from my site in case you cannot find it. Moreover, in the repo that you guys are creating and cloning, it also has a files folder or docs folder that also contains this information. All right, so all information is there. So in my site here, in the legacy part, in this lesson that talks about interacted with the port and pin, lesson number 7, which I'm going to bring to the new 1250 very soon, maybe later today or tomorrow. So it will be available on this 1250 part, because we'll start discussing this with the 1250 section. So those sections run mostly, I can probably quickly pull up here. They run at this time. So I'm doing 2 sections of 1250, and those run on 7 to 9 Monday, Wednesday, and then 6 at Friday, same as this other one here. So if you ever have time and want to join any of those sessions, you're welcome to come and maybe ask questions while we're in the work period. If something is not clear, okay? So that's extra time to get a helping person. So, but basically, since the first library that we need to create is a GPIO library, the first thing we need to understand is how the GPIOs work, okay? And again, if you see this part 2 here, the first 2 things that it says, even though this is using the older micro, the G031, the registers and everything are the same. So the code is absolutely portable. So the first thing I do here is to enable the power interface and then enable the clocks for the peripherals. That is exactly what I have here, okay?
Yes.
And then here comes the first step. To use a pin, so we have to, just a second. We have to first set up this motor register. In this motor register, we have to tell if the pin is going to be an input, a general purpose output, or an alternate function, or is it going to be analog? An alternate function is to use it with other pins like the UART or the SPI or I2C. So in this particular case, we want to do it as a regular GPIO, general purpose output. So we really want to write this configuration. Now, since these are 4 possible combinations, so we actually need 2 bits to configure this. So that's why the register is 32 bits. So there's 2 bits per pin. Okay. Now, if we go back to the schematic, so what we're going to try to do here is going to try to toggle this LED, right? So which is PA5. So we're going to go here and in our infinite loop, well, first we're going to say configure PA5, which is LD4, right? Is the LED, the built-in LED, as a GPIO output. Okay, so that means that the motor register needs to have what?
0, 1.
0, 1, excellent. So
Yeah.
it seems like you've been already studying.
Yeah. I have to prepare for that.
Oh, okay. Okay, that's good. That's good to know. Yeah,
Okay.
0, 1 is general purpose output. Yeah, 0, 1. Now, this 0, 1 needs to be obviously in the proper location, in the location of GPIO 5, which if we go to the reference manual, let's just go to that. This is the reference manual? No, this is the data sheet. Let's just open the reference manual from here. So GPIO was chapter 7, and then we go to the registers, and then we're going to the motor register, which is this guy. So we want to add a 0, 1, but we wanted to add to bit 5. So 1, 2, 3, 4, 5 here. So in reality, what I need to do is, in thinking, this is already thinking about the library. So I need to target this register. I'll show you what I do here.
Yeah.
So GPIO A pointing to motor. And then what I want to do first, I want to clear the settings there in case something is already written in there. So I want to have that clear. And think about this. 0, this is how we write in binary. So this is going to be a bit shifted to the left by 5 times 2. Why is going to be a bit shifted by 5 times 2? I'm not so sure if this is going to do the bit shifting first or the multiplication, so I'll put another bracket there. It's because since there's 2 bits per pin, and we're talking about GPIO 5, it needs to be actually bit shifted to the left by 10. So if we go back and look at the thing here, see if you start here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you want to do this guy, right? Yeah. So that is the way we do it. So this one is just going to clear the settings. Okay, and now to actually write the settings that we want to do the 0, 1. So in this case, we do it with or equals, right? And instead of doing it, we do the same thing, but instead of doing the complement, we no longer do the complement. We do the 0, 1, and we do that. Okay?
Okay, yeah.
All right. So let's give it a try. So we're going to run this thing. We can actually debug by putting a breakpoint there. What I just did was to put a breakpoint. Now, to actually look at the debugger, since there are so many registers, they're all in these groups here. So they have to be enabled. And in this particular case, we want to take a look at GPIO A. So we're going to enable that one. And in particular, now it shows up here. In particular, we're going to expand this motor register. So this one, this motor 5, should change after these 2 lines. As you can see, it's defaulted to 3, which is 1, 1. Okay, that is why I clear the settings first. I'm going to run this. It's going to stop there. Now with F10 or pressing here step over, I can actually go to the next line and pay attention to this. What happens after this it clears. See, it goes back to 0. And then after that, I'm going to do the setting 0, 1. So if we look, now it's a 1. That means that it wrote there the pin now as an output, and I can use it as a regular GPIO output. Okay. Some interesting thing to note here. If for some reason you forget to enable this in the clock, let's say you forgot to enable the GPIO-A, this is exactly what's going to happen. And this will give you a hint. So we're going to run again this, and we're looking at motor 5. And now I'm going to step over and look at that. Nothing happens. It doesn't change. And why it doesn't change? Because it's not enabled here. So this is when you're debugging, that's why debugging here is important. The debugger is really good for this micro. When something doesn't work, you need to say, oh, maybe I forgot to enable the pin. Okay?
Yeah.
Now, in this motor is how we enable the settings of the pin. Now, how do we actually toggle that? Well, I need to first create an infinite loop here, so I can do with while 1. And the easiest way to toggle a pin would be targeting the ODR register. And let's go back here to this lesson, which I think I lost it. I don't know where I had it. Oh, because I opened this guy, right? Well, we can always go from here back to the lesson. So that was this one. So after we configure it as an output, see, now we can toggle, well, we can clear, all the information is here. And we target the ODR register, okay? Let me just, I'm gonna have to open this in a different window so I can always have it. Okay. Yeah, so let's go back to chapter 7, register ODR. ODR stands for output data register, and to read a pin, we use IDR, which is input data register, okay? So they're very good at with the naming. So in this particular case, this register is simpler because it only uses 16 bits. So basically, you just write a 1 or a 0, depending on if you want the pin to be off or on, okay? So all we have to do here is just to set or to toggle this particular pin, the bit 5. So what we're going to do here to toggle, again, we're going to do GPIO-A pointing to ODR, and then we're going to do exclusive OR, and what we're going to do, we're just going to do a simple binary 1. Now, for this, we can actually use also masks. There are masks for this, like if we go GPIO underscore ODR underscore OD0, or what, OD5 in this case. Yeah. We could use those, but since I'm doing this more thinking about building the library that you're going to build, or in case you have already maybe built, I want to do it with the bits and the bit shifting. So this, in this case, is not going to be bit shifted by 5 times 2 because it's only 1 bit. It's just going to be 5. And this is going to toggle the pin. Okay. Of course, if I toggle this, this is going to toggle like crazy fast. Okay. So I want to slow it down a little bit, maybe doing a for loop there. Yeah. So I'm going to include this library that is actually very useful in this micro that it wasn't supported in the other one, which is the stdint.h. And this library allows us to have this declarations, because since the integer in this micro is not 16 bits, it's 32, sometimes we want to make sure that we declare a variable as 16 bits or as 8 bits, and this will do it. Okay. So in this particular case, I want to do a 32-bit variable, and I'm just going to call this one delay and maybe make it equal to 500,000 because it's a 32-bit number, so we'll hold that. And I'm going to say here while minus delay. Okay. So that means that this thing will hold it there and decrementing until it reaches 0, then it's going to toggle. So if we run this thing, we should be seeing that thing toggling. Let's see. Yeah, it's actually toggling there. You can probably see it. It's a lot of reflection from the light, but yes, the LED is actually toggling. So I can control actually that particular pin. Okay. Any questions up to this point?
I'm pretty good now, but like how long is the delay? The delay is file with a lot of zeros, but like how can I know how long is the real
Yeah,
time?
at this point, I don't have a anything set up in terms of there's an assignment that we had to determine how many delay cycles we had to do per second to get a 1 millisecond and then go from there. But I think at this point that is a bit unnecessary, because then when we started covering timers, it's much simpler to actually get that done through a timer or through the SysTick timer that we just discussed now in class with the interrupt. So there's no much point in trying to get this working with delay cycles. I rather encourage you guys to focus on building the
Time.
libraries.
Yeah.
Okay?
Okay. Yeah. Good.
Yeah.
Thank you.
Yeah. So the libraries, talking about the libraries, I know this is very introductory and a super fast track. So I'm going to do uh, at least a couple more sessions of this. But at the same time, I need to start fast because you guys need to, so you don't fall behind, right? And I don't know if you've
Yes.
gone to the Thursday sessions, but Simon is also helping during tutorial time.
Okay.
So in here, in the content, I added in the important resources, maybe? Yeah. So I added here a couple of things. So there are notes from Simon from last term, all the notes that he wrote there here, okay? There's also the library headers. His headers compared to mine are a bit different because we ended up creating different headers. You decide which ones make more sense to you. I'm not really going to force you to use either or. In the notes, of course, the notes on my site have everything that I've shown you, but he also has his notes. So let's say if you want to go with my libraries, so the first thing you want to do is to implement your GPIO. Okay.
Okay.
And this is going to be, I guess, a bit tricky, and we should probably talk about, make a stop at the code here, and talk about the actual repository creation. So you should have already created your repo, I believe. So let's just go here. Let's see if mine is created. Yeah, mine is already created here, so I'm just going to clone it. And I'm going to put it in. I'm going to put it in. Is this 2020 or 2250? I'm going to put it here in code. I'm just going to put it there. Okay. So that's going to clone my repository for this term. Okay, for my own purposes. And one of the first things you got to do here, that I think I did show you that in class, you have to go to File, Add Local Repository, and actually add the repo that is inside because it's already part of it as a submodule. And select this folder, in-class demos, and that's going to bring up the in-class demos repository. Remember to change this to the main branch so it doesn't get corrupted. So all the demos are going to be in here. So once this is done, you can go back to your main repository and maybe do a commit and push here to sync them. The way to know if the syncing is working, you just go on GitHub, and when you click on this in-class demo that has an arrow here, should take you to the actual in-class demo repos, and it should show the demos there properly, okay? But in this case here, you have this repository. You can open it with Visual Studio Code if you have Visual Studio Code installed. And the first thing you got to do in this structure inside your libs and inside your ink folder, you got to bring down all the libraries that you're going to implement. Okay. So if we look at the GPIO library, which is the first one that you should work on. So this one is defined here. So see, we got an init input and an init output. So, and what you got to do is to go the proper C library for that. Let's say I'm going to add a new file, and I'm going to call it just underscore GPIO because I already have mine, right? But you should call it GPIO.c, but I'm going to call it underscore GPIO.c. And what you do, you put this on the right side and you start implementing your library. For example, init this as a GPIO output. And in fact, Copilot can help you here because as you can see, it's already suggesting code, but you got to make sure that you understand what Copilot is trying to do because sometimes it makes mistakes. So I'm going to include, what do I need to include here? The first thing I need to include is, of course, not that one. See, it's trying to suggest something that is not right. I'm going to include GPIO.h. Okay.
Yeah.
And I'm going to do the GPIO init output. Sometimes the Copilot is annoying because it starts typing, and doesn't let you. So the first thing you want to do here is exactly what this is saying here. Set the corresponding motor bits to 1. So you're going to go, I need to put actually the names here. So this is going to be the pin, and this is going to be the pointer to the port. Okay. So I'm going to do P port pointing to motor. That is correct. Okay. But before we do that, we need to do the thing that which clears, right? And right after that, then we set it to output. Okay. See, this is the same thing that I did in the demo. So at this point, your GPIO should be included. Now, the VS Code doesn't want me to show this properly here. It's just because of a glitch, because Microsoft has a GPIO thing, and it kind of conflicts with that. But in Seger, this will work fine. There's a workaround for fixing that too. For setting your GPIO input, it's the same idea, very similar. The only difference is that instead of doing 0, 1, I think you leave it as 1, 1. Is that the case? I can't remember. No, analog is 1, 1. General input will be 0, 0, 0. So
yeah.
Actually, general input will be easier because it will be just typing this first line here. By clearing the bits, you already have it. Let's use a P port. And then this will be pin. Yeah, so just by doing that line, your pin is already set up as an input. Okay?
Yeah.
And that is how you're going to start creating your library for the GPIO. There's a GPIO read, and the GPIO read, how do you read? Well, we can probably do that. If we look at the schematics, because we do have a user button. So let's take a look at the schematic. So the user button is located, let me see. This is the reset switch. That's not the one. It's this guy here. And it's connected to PC13. Okay? Now, this button, if you notice, is active low. So it pulls high, and when you press it, it brings it to ground. So it's going to have the opposite as we are used to. So PC13. So I'm going to say here, blue button is PC13. Okay. So we're going to configure this one now as input. Okay. So we have to clear the settings, same as here, but in this case, it's going to be GPIO C13. Okay. So that's going to be 13 times 2. Okay. Set as input. Okay. And GPIO C is already enabled here. No, it's not. See, I need to enable GPIO C, otherwise it won't work. And that would be by doing this.
Okay.
And at this point, this thing is already configured as an input. And how can I check? Well, similar to while doing the other micro, and that gets done looking at the input data register, the IDR. And if we go to the registers here, IDR, see, it's also 16 bits. So all we have to do is just check if that is a high or not. So we're going to do a masking with AND, and then we're going to do this is 13, right? So we're going to do this. We're going to AND it with 0B1. Bit shifted to the left by 13. Not 123, 13. So if that is the case, we do something. If that is not the case, we do something else. Okay. Now, the button pressed is not going to be when this is detected high, because remember, this thing is active low. So here is when the button is pressed. And when it's detected high here, this is button not pressed. Now, of course, I need some sort of state variable if I want to do this only once per press. So maybe I should declare here something like uint 8 underscore t. I'm just, oops, I'm with caps. Uint 8 underscore t. I'm going to say press, and it's just going to be equal to 0. Okay, so I'm going to use a simple state variable, not the whole state machine. So I'm going to say here, if the button is not pressed, then set this one to pressed. Okay, and on the release part, the button is not pressed. So in this case, we're going to say button just pressed. And in this other one, we're going to do something similar, but it's actually the opposite. And when this is detected not pressed, we're going to check if the button is pressed. And we're going to set it to 0. And we're going to say button just released. And the way we're going to do this, we're going to send something to the virtual console in this case. We're going to say printf, and we're going to say button just press, and we're going to do a \n. And in this other one, we're going to say button just released. No, that one is just released, sorry. And this one is just pressed. And that should do it, actually. It's just that now with this delay, it may take a while to detect the button as pressed or released because it's inserted inside the delay, but let's see if that works. And I'm going to press the button, and let me see if I can show the camera on the other side. Okay, so here we go. Button just pressed. Look at that. Let it go. Button just released. Button just pressed. Button just released. Make sense?
Yes,
See,
yes.
This thing can help us. It's better than the other micro in the sense that we can do a simple printf and we can see it in this console. Okay.
Yes.
But it only works when we're debugging, right? But later on, when we enable the UART, we can actually see that. Okay.
Okay.
Now, one important thing here. Let me just move this project to inside this project that I just created. I just closed it. Code samples. I'm going to move this demo project and I'm going to put it inside my repository. So this is what you should do. Your ICAs are going to go here. So I'm going to create a new folder. That's going to be called practice. Okay. And I'm going to place this project here. So I'm going to open this project. And you double click on the project file, actually, which is this one. Now, and it gives you this window at the beginning that tells you about the license and blah, blah, blah. Let's say I now want to start using my libraries. So I want to include my GPIO library. So when it shows a red squiggly, so remember the green one is that you're not using the library. The red one is that it can actually not find the library. And the reason for not finding the library is because in here, you need to set up the path to the libraries. And that is why it's important that your folder structure behaves the same way. So in your ICAs, you're going to have ICA 1, ICA 2, blah, blah, blah. In your labs, you're going to have inside lab 1, lab 2. Remember, you have to create the folders. And for practice, the same thing. So actually, to find the libraries from the location of where this project is, I need to go one level up, 2 levels up, and then look for this lib folder, and ultimately for this inc folder that contains all the H's. Okay, so it's 2 levels up. So what are you going to do here? You're going to right click on the project and say options. And then you're going to go to a preprocessor. And then you're going to look for user include directories. And then you're going to type double dot backslash one level up, double dot, another backslash, two levels up, then look for the lib folder, and then look, another backslash, look for the ink folder, which in my case, I have the libraries separated in ink and SRC. You may decide to have everything in the same folder. It's up to you. And when I hit OK, see, my GPIO no longer shows as a red squiggly. So that means that I can actually use this library. Okay?
Yes.
Now, this works, but I'm not yet using the library. But if I wanted to use it, let's say I wanted to call the library and do something like GPIO underscore init output. And this is the way it's going to work. Let's say I'm going to use GPIO B and pin 3 to set it as an output. And see, this is how this is going to start working out once you code your libraries. The moment I want to do that, this is going to complain. And the reason is because even though the library is properly included, the path is added. So I'm forgetting one important step, which is the same step that we had to do in Code Warrior, which is actually adding the source files here. So any library that I want to use, I need to drag and drop the source file, which in my case is my GPIO. So it needs to go there, right? And now if I do that, I can run this properly, and it's now going to start using my libraries. All right?
Yes, that's good.
Okay. So with all these steps that we did, a super like fast track thing, we're good actually for doing most of the stuff. Okay. Now, there's maybe one thing, because I have another 20 minutes that I can discuss. And let's go back to the lesson here. Is that so far we know how to use this as a GPIO. So by default, this is set as a GPIO input. If we want to set it as an analog pin that we will look later when we learn the ADC, we have to set it to 1, 1. For output, we know that already that has to be 1, 0. And for alternate function is 1, 0. So what are the alternate functions? Well, the alternate functions are for using the pins for other things, because the pins are actually multiplexed. And how is the best way to look at this? The best way to look at this is actually installing this tool. If we go to tools and documentation and we go to the ST tools, we look for the STM32 CubeMX. And once you install that, you actually eventually have to create an account with ST, unfortunately. You open this STM32 CubeMX, and that opens this tool. Now, this tool is for auto-generating code using the vendor libraries. That's not what we're doing in this course, because we want to use bare metal, because we want you to understand what's going on with the registers. But this tool can help you actually look at the pins and the signals that you have available. And I'll show you how you get started with this. So you can start a project with going File, and you say New Project. And then you can save this so you can recall it after. So I'm going to probably save this after I'm done. So the best way to go about this guy is to do the board selector, because if you go by micro, you got like hundreds of micros here. So you go board selector, then you choose your Nucleo 64, because this board is a Nucleo 64. Then you go to the MCU MPU series and you look for the STM32G0. And then you have only 3 options, and your board is actually the G0B1RE. You can double click on this one just to set everything peripherals to default mode. And this brings up this interface here. And it shows you all the pins. And this thing can generate code, but again, we're not using that. But it's very interesting, for example, for looking at the clock configuration, how you can get the clock using the PLL, for example. And what are the numbers that you need to put in this M, N, and R to get, for example, 64 megahertz or 40 megahertz. You can play with these numbers, for example, see, 40 megahertz, but when it shows in red, it means that you cannot use those numbers. Okay, so this will help you code your clock library, but we're not there yet, so I'm gonna set that to default. What I wanna tell you here, for example, in this particular board, the equivalent to the SCIs that we have in 1250, these are called USARTs here, and they are shown in connectivity. See, we have so many users. We have user 1, user 2, all the way up to user T6, and we have 2 low power UARTs. So we have like 8 different serial ports. Now, why is this user 2 already marked? Because the user 2 is already connected on this board. Since we said at the beginning, set everything to default, the user 2 is the one that goes on the USB port, and it actually goes to this particular COM port here, which is the COM4. Okay. Now, how to set this user 2? It is already telling you that this user 2 is available by default in PA2 and PA3, because that's how it's actually defined in the schematics. If we go to the schematics, that I don't know where I put them, I think I lost them, but they will show you that they are defined and on those pins. Although, if you hold the control key and click on one of these, it will tell you where else you can have the same signal. Okay. However, this one, you don't want to move it because this user 2 is physically connected to the USB. So you cannot change that. But let's say if you wanted to use user 1, for example, you want to enable another user and connect, wire up something in there. You set this one as asynchronous, and it brings up these other 2 pins, PC4 and PC5. Now, these ones, if you click on these pins again, if you hold control and click on one of them, it's going to show you where else you could have that. You could also have it in PV6 or PA9. So you could potentially move this user 1 TX to this pin, see? And in these pins, it will show you all the possible signals that you can have there, okay? And the question is, how do you set this up so it uses PA9, right? And that is what the alternate functions are. So the first thing you have to do to use the alternate functions, oh, this is where I had the schematics. Maybe I should show you where that is. So see, use our 2TX, PA2 and PA3, and that goes actually to the USB eventually, okay? So I think in the lesson here for the user is lesson 9 from the old run that we did of this course last term. It tells you all the steps to set up the users. You can actually build your own libraries just looking at this because it's very clear. But one of the important things here is that, I don't know if in the steps I think I call it here. Lesson 10 talks about the alternate functions. So the alternate functions, the way they work, so the first thing that we got to do is to set the motor to alternate function. See, instead of now doing the 0, 1 that we had before, we need to do 1, 0 to set it to alternate function. And then after we do the alternate function, now we need to go to another register, which is the AFRH or AFR low. I think this one is not shown properly. This is how it's shown properly. This register in particular is set up as an array of 2 registers, where the 0 is the low part and the 1 is the high part. And why is that? Because the alternate functions use 4 bits. So since you have 16 pins, 4 times 16 is 64. So you actually need 2 registers. So 1 is not enough for setting this up. Okay. And if we go to the reference manual, we'll see that. Let's go to the GPIO registers, to the alternate function. As you can see there's alternate function low and alternate function high. So the alternate function low will handle, where is that one? Here. Will handle from GPIO 0 all the way up to GPIO 7. Okay? And the alternate function high will handle from GPIO 8 to GPIO 15, which is why in this lesson here, I do have this set up here. So this is what you should have in your library. You check if the pin is less than 8, it goes into this guy. And if it's 8 or more, it goes into this other guy. And the way you gotta do, you gotta clear the 4 bits and then add the proper alternate function there, just the same way we did with the other register. Now, where do we find these alternate functions? We need to go to the data sheet. We go to the pinouts and we go to the very end here where it shows alternate function mapping. And these are here. And how do we make sense of it? Let's go back to this. So let's say I want to use user one, and I want to move this one also out of there because I want to have it next to the other one. So probably PA10. Yeah, I'm going to put it there. User one RX. So I actually need to set PA9 and PA10 to work with user one. So I'm going to look in here this alternate function for PA9 and PA10, and I'm going to see all the alternate function settings. See, this could be timer 15, it could be I square C. So we're going to set it to user one. So we need the alternate function one. Okay, so that means that in the PA9 and PA10, which are actually going to be these registers here and this one here, right? We need to put a one, and it has to be bit shifted accordingly. And that happens according to this formula that I have here. Okay? And only after we do that, and of course, if we wanted to use the USART, we also need to enable it here. Okay? Because it also needs to be connected to the clock. Now, it might be a little bit tricky to find where the USART is in here. I know this is in the reference manual somewhere, but let me see if I can pop it up from here. No, it won't work actually from here. Maybe when from VS Code. VS Code is better with the IntelliSense actually. Let me see if I can go RCC USART. Yeah. Yeah, so if I want to enable the USART here, see, the USART is enabled in the APBENR. So this is the line, it's already telling me here. So I have to actually add it in this line. It wants to add now the GPIO. See, it's a different register. See, the power interface is in here, is in the same register, is a USART. This is USART 2. That's not what I want. I want USART 1. But USART 1 is on a different one. Let's just type it again. RCC underscore USART 1. It's this guy. Is in APBN and NR2. Yeah. Yeah, so that needed to be enabled here. So I would say
the comments should be enable you start one clock.
Yeah, to use USART 1, do this. So first, enable the clock. It even shows what it is. Then secondly, configure alternate functions. So we said that we were going to use what? PA9 and PA10. So we're going to do PA9, USART1 TX, and PA10 USART1 RX. So the way we're going to do that is we're going to go into the alternate function and do it correctly, okay? And I think it's already telling me.
Yeah.
Yeah. See, it's already using the same formula, but you know what? This is forgetting to clear the settings. So let's clear the settings first. So we gotta do this guy. And then we clear, but it has to be with all ones, or you can do an F instead if you prefer in hex, right? Yeah. So then same thing. Oh my goodness, Copilot wants to erase the whole thing. And this one should be, 10.
10.
Yeah. And that way it clears clear settings. And you're going to have to do this for your libraries, right? So you're going to have to somehow implement this in your libraries, in your GPIO library. Well, I think this is more than enough information for today. So in your particular case, I'm not sure how far you are. I think you told me that you already coded the libraries or something.
I create GPIO library, but I didn't start USART. Yeah.
Okay, so at least get the alternate functions going because I put those as part of my GPIO library. See, in it alternate functions here. So once you have that one, then we can move on to the USART library. Now, for all the USART configuration, you can go again into these legacy lessons I have here, All the information is here, but I'm going to soon update this and put it in my 1250. Okay.
Okay.
The other thing I'm going to do is I'm going to give you access to this repository, for all the demos from last term for 1250. So you can also get information from there. Okay.
Okay, great.
Yeah. So let me do that right now. So before I forget, so let's go to GitHub. First I need to go to the classroom for the 2250, which is here, right? Yeah. You should be somewhere in here. This is you, right?
The first one, yeah.
Yeah. Okay. So we're gonna go to this 1250 organization. Oh, this is too big. Yeah. 1250. And I'm gonna look at the teams, and I'm going to create a new team here. And it's gonna be called 1252, and it's going to be STM32 fast track. Okay. Okay. So what I'm going to do, I'm going to add you to this team, and I'm going to add everyone else who needs the help. Unfortunately, nobody else is here, but yeah. Also, you already added. That's great.
Yes.
How come?
I don't know.
You were already in this organization probably from 1250. Okay, so what I need to do now is for this team, you're yet still not seeing the repo. I need to share the repo. So in class demos. So I'm actually going to add you to this semester's demo, but most importantly, I'm going to add you to last semester's demos, which are all these ones here. See, you can all use all these ones to help you create your libraries and collaborators and teams. So I'm going to add a team here. So 1252. Oh, no, sorry. I need to go add team. 1252 STM32 fast track, read access only, unfortunately. Yeah, so this one is the in-class demos from last term and the in-class demos from this term, which already has a couple of things here, but nothing too advanced yet. I'm also going to add you here so you can see things going on from this term. So 1252, no, sorry, add teams. So let me know once you accept the invitation to the organization, if you can see these repos. You should be able to see them in the 1250 organization. So when you go to, you should be able to see these repositories aside from whatever else you were seeing from 1250.
Yeah.
Okay.
Okay. Yeah.
Yeah. So those already have information there for you to kind of keep working, and for everybody else who's going to be watching this later. Okay.
Okay. Thank you for your time, sir. Yeah.
Yeah. I think with this, I gave you enough to keep working on, and then I'll probably do another section, at least a couple more Saturday, just to look at the other peripherals like the timer, the UART, and all that.
Yeah. Yeah. Sure. Thank you. Okay.
Yeah. No problem. We're going to start the recording here.
Okay. Have a great one, sir. Yeah.
You too. Thank you.
Yeah. Okay. Bye.
Bye.